Hello, everyone, and welcome to Kilowatt. My name is Bodhi, and I am your host. And folks, we are here to talk about Tesla AI Day. I knew Tesla AI Day was going to be on Friday, September 30th, but what I didn't realize until very late into the game that they weren't going to start until 6 p.m. It was like 6:15 p.m. California time, which means Tesla always starts late, so it's like 6:45. This thing went 3 hours, and yeah, it's a lot. There's a lot of information in here. I have to tell you, I did very heavily edit this down for some good reasons. One is I don't want this podcast to be 7 hours long. Two is it's very technical. Like, you know what? Let me just play a clip. Let me play a clip, and you can see how technical it was.
You cannot just do training with just videos. Of course, you need some kind of a ground truth. And that is actually an interesting problem as well. The objective for storing your ground truth is that you want to make sure you get to your ground truth that you need in the minimal amount of file system operations and load in the minimal size of what you need in order to optimize for aggregate cross-cluster throughput. Because you should see a compute cluster as one big device which has internally fixed constraints and thresholds.
You know what? If that made sense to you, which it did make sense to me, I have another one I can show you. Let's go ahead and listen to the other one.
As you can see, it takes the massive graph of neural nets with 150K nodes and 375K connection, takes this thing, partitions them into independent subgraphs, and compiles each of those subgraphs natively for the inference devices. Then we have a neural network linker which shares the structure to traditional linker where we perform this link time optimization. There we solve an offline optimization problem with compute memory and memory bandwidth constraints so that it comes with an optimized schedule that gets executed in the car.
So if you didn't understand that, I don't know what your problem is. It was very clear. Very clear. Anyway, my point is this presentation was to recruit smarty pants engineers and scientists to work on this kind of stuff for Tesla. This was a 3-hour recruitment presentation. I am not a smarty pants engineer or a smarty pants scientist or even just an everyday smarty pants. I'm just kind of an average pants kind of a person. So what I did was I heavily edited this so that you get the information that you need, because I know that I have a very nerdy audience. I know that there are some people that are listening to the show right now that understand a lot of what he just said. So what I tried to do is I tried to meld the two together where I give you some good information, but it still makes sense. And a lot of the stuff that they talk about in this presentation heavily requires the visuals to make any sense out of it at all, unless, you know, like I said, you're very familiar with this kind of stuff. So I'm going to do my best to explain it, but I think the clips that I've pulled are pretty good for the goal of this show. And I have to say, even though I didn't understand a lot about what they were talking about, I did understand some of it, and it was really very interesting. And my kids actually sat down and they watched some of the presentation as I was pulling the clips with me. So they actually enjoyed it and had a lot of really good questions. Really good questions that I really wasn't able to answer a lot of those. But yeah, it was good. Just some technical information that you should probably know before going into this. They talked a lot about the programming language Python. They're using Unreal Engine 5 and a lot of the simulation type stuff. If you don't know what that is, it's primarily a video game engine used to create some of your favorite video games, but it's also used for more utility purposes like, you know, science and engineering and stuff like that. So it's a really powerful tool for a lot of different reasons that I won't go into here. And then finally, they talked a lot about the proprietary Tesla hardware and software, which you're going to hear a lot about. Even though it's heavily edited, this episode is going to be jam-packed with information for sure. I have 11 pages of notes just on this presentation alone, which is insane. Just some other quick announcements before we get going. Elon announced that Tesla AI Day is going to become an annual thing, and Tesla might actually start releasing a monthly podcast. So that's pretty cool. I look forward to that. And then we have some breaking news. We have Tesla's Q3 2022 delivery numbers. The Model S and Model X, they produced 19,935 Model S and X's. They delivered 18,672 Model S and X's. Of the Model 3s and Ys, they produced 345,988 Model 3s and Ys, and they delivered 343,830 Model 3s and Ys for a grand total of 365,923 vehicles produced Q3 2022 and 343,830 vehicles delivered during the same time period. Now, Tesla's earnings call is coming up. It's October 19th at 4:30 Central Time. And as always, we will cover it here on this podcast. Let's go ahead and jump into Elon's opening remarks.
Welcome to Tesla AI Day 2022. We've got some really exciting things to show you. I think you'll be pretty impressed. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot suit. But we've come a long way, and it's I think compared to that, it's going to be very impressive. And we're going to talk about the advancements in AI for full self-driving, as well as how they apply to more generally to real-world AI problems like a humanoid robot, and even going beyond that. I think there's some potential that what we're doing here at Tesla could make a meaningful contribution to AGI. And I think actually Tesla's a good entity to do it from a governance standpoint, because we're a publicly traded company with one class of stock, and that means that the public controls Tesla, and I think that's actually a good thing. So if I go crazy, you can fire me. This is important. Maybe I've gone crazy. I don't know. So we're going to talk a lot about our progress in AI, Autopilot, as well as the progress with Dojo. And then we're going to bring the team out and do a long Q&A, so you can ask tough questions.
So nothing really huge in terms of Elon's opening remarks. We didn't get any bombshells here. As he said, the way that the presentation is laid out is we're going to talk about TeslaBot, and they had an hour to talk about TeslaBot, an hour to talk about FSD and Dojo, and then it was about an hour for questions. So it was jam-packed full of information. One of the things that I would like to talk about real quick before going on to our next clip is Elon said on stage several times throughout the presentation that if you don't like what he's doing or what Tesla's doing, Tesla's a publicly traded company. They only have one type of stock. You can just, buy stock in Tesla and then, vote to make the changes. The thing that he doesn't really mention there is that almost all shareholder votes end up failing. It's a little harder than he's making it seem. Like, if you don't like what I'm doing, you can just fire me, is one of the comments that he made in this last clip. Well, that's not exactly true, because a lot of people don't like what they're doing, and they've done various things to try and change things at Tesla. And despite best efforts, those things haven't passed. Like, if somebody if a bunch of stockholders got together and they said, let's say 15 million stockholders got together and they said, we want to fire Elon. And each one of those stockholders had one share of Tesla, and they all voted to fire Elon. Well, I'm pretty sure that Elon Musk has more than 15 million shares of Tesla, and he could easily just veto that. And he's like, nope, we're not going to fire me. You know what I mean? It's more complicated than he's making it sound. Now, having said that, let's move into our next clip. Just before I play it, I want to set the stage here. There's going to be two additional engineers on stage. I think one of the engineers' name was Imam. although it was really hard to hear it in the video. So I apologize if I got it wrong. And the gentleman is a autopilot engineer, and then Lizzie, and she is a mechanical engineer. So they're going to show off the bot for the first time. The bot comes out on stage. It does, some electronic music. It's walking slowly, and it walks around the stage, waves to the crowd. It does some dancing. It was, wasn't like the coolest clip ever, but one of the things that was cool was the first time that this bot actually walked without a tether, which is something that's going to keep it from falling down. So it was a little bit of a risk for Tesla to let it walk around on stage, but it didn't really do very much. So they had a video that showed the bot watering plants, picking up boxes, moving things from one shelf to another, moving parts like on the factory line, moving parts from one box to another box, that kind of thing. All this stuff doesn't translate from video to audio well, so that's why I'm describing it to you. Oh, and they had two bots that they showed off. One looked like Johnny Five's. If you don't remember who Johnny Five is, look him up. He looked like Johnny Five's super cool, hip cousin from like California. And the other one looked more sleek and more like the Optimus robot that Tesla showed off last year, or the concept that Tesla showed off last year. But the newer one, the concept one, that one can't walk around or anything. So the one that we were looking at, or the one that actually did something, was the Johnny Five's cousin one. So if you haven't seen it, I highly suggest taking a second to Google search it. It's actually pretty neat. All right, let's listen to Elon talk about the cool concept, not the Johnny Five bot, but the much cooler concept bot.
So here you're seeing Optimus with these are with the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. And we've also designed it using the same discipline that we use in designing the car, which is to design it for manufacturing such that it's possible to make the robot in high volume at low cost with high reliability. So that's incredibly important. I mean, you've all seen very impressive humanoid robot demonstrations, and that's great, but what are they missing? They're missing a brain. They don't have the intelligence to navigate the world by themselves. And they're also very expensive and made in low volume. Whereas Optimus is designed to be an extremely capable robot, but made in very high volume, probably ultimately millions of units. And it is expected to cost much less than a car.
I'll just bring it directly to the right here.
I would say probably less than $20,000 would be my guess.
So you can hear them kind of talking in the background, like, let's just move it to the right here. What was happening is they had to wheel this concept robot out onto stage, and then like 3 people stood around it to make sure it didn't fall down. And then they just kind of wheeled it off to the right of the stage so it could stand there while they were doing the presentation, but it wasn't in the way. I will say watching the fingers move was pretty neat. I'm not an expert in, robotics, but it seems like a lot of these robots just kind of have a claw, and that claw, performs some sort of specific utility. The Tesla bot is more designed to interact with, like a human environment, where whether that's, your backyard raking leaves, or if that is in a factory moving boxes from one place to another, or, bolting on doors, for instance. I don't know if that's really what Tesla bot's going to be doing. I do think it's really cool that this is going to be less than $20,000. I would like it to be less than 10, but less than $20,000, that's pretty cool. If Tesla is able to make this do all the things that they say that they can, in terms of, it can work in a factory, it can work in your home, it could be your friend. If all of those things are possible, I'm aging, I'm almost 50, I'm 47. getting really close to the point where maybe I don't want to be cleaning my house, but I want a clean house. Would I spend $20,000 for a robot to do that? Maybe, if I can afford it and it did a good job. If I'm being honest, what I'd really like to do is I would like to create a business with Tesla bots and Tesla self-driving cars, and the self-driving car drives the Tesla bot to your house, cleans your house, you pay me $200. The Tesla bot gets back in the car, drives to the next place, cleans their house, I get $200. That would be really nice. Pie in the sky, but there you go. A free business idea for you. All right, let's go ahead and jump into our next clip.
So, now there's still a lot of work to be done to refine Optimus and improve it. Obviously, this is just Optimus version 1. And that's really why we're holding this event, which is to convince some of the most talented people in the world, like you guys, to join Tesla and help make it a reality and bring it to fruition at scale such that it can help millions of people. And the potential, like I said, is really boggles the mind, because you have to say, like, what is an economy? An economy is sort of productive entities times their productivity, capita times output, productivity per capita. At the point at which there is not a limitation on capita, it's not clear what an economy even means at that point. An economy becomes quasi-infinite. So, what taken to fruition in the hopefully benign scenario, this means a future of abundance, a future where there is no poverty, where you can have whatever you want in terms of products and services. It really is a fundamental transformation of civilization as we know it. Obviously, we want to make sure that transformation is a positive one and safe. But that's also why I think Tesla as an entity doing this, being a single class of stock, publicly traded, owned by the public, is very important and should not be overlooked. I think this is essential, because then if the public doesn't like what Tesla's doing, the public can buy shares in Tesla and vote differently. This is a big deal. It's very important that I can't just do what I want. Sometimes people think that, but it's not true. It's very important that the corporate entity that makes this happen is something that the public can properly influence. So I think the Tesla structure is ideal for that. And like I said, self-driving cars will certainly have a tremendous impact on the world. I think they will improve the productivity of transport by at least a half order of magnitude, perhaps an order of magnitude, perhaps more. Optimus, I think, has maybe a 2 order of magnitude potential improvement in economic output. It's not clear. It's not clear what the limit actually even is. But we need to do this in the right way. We need to do it carefully and safely, and ensure that the outcome is one that is beneficial to civilization and one that humanity wants. This is also extremely important, obviously. So, and I hope you will consider joining Tesla to achieve those goals. At Tesla, we really care about doing the right thing here, or aspire to do the right thing, and really not pave the road to hell with good intentions. And I think the road to hell is mostly paved with bad intentions, but every now and again there's a good intention in there. So we want to do the right thing. Consider joining us and helping make it happen.
All right, Elon has said this in the past multiple times, so I don't know that there's a lot of need for me to talk about it again, but I did think it was important to revisit and hear it again in his words. Let's go ahead and jump into our next clip. And Lizzie, the engineer, the mechanical engineer, we didn't get a last name for her. She is going to get very geeky, and we're going to learn more specifics about Tesla Bot. So let's go ahead and jump in.
All right, so you've seen a couple robots today. Let's do a quick timeline recap. So last year we unveiled the Tesla Bot concept, but a concept doesn't get us very far. We knew we needed a real development and integration platform to get real-life learnings as quickly as possible. So that robot that came out and did the little routine for you guys, we had that within 6 months, built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. So this guy is rooted in the foundation of sort of the vehicle design process. You know, we're leveraging all of those learnings that we already have. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form. We think that matters for a few reasons. But it's fun. We spend a lot of time thinking about how amazing the human body is. We have this incredible range of motion, typically really amazing strength. A fun exercise is if you put your fingertip on the chair in front of you, you'll notice that there's a huge range of motion that you have in your shoulder and your elbow, for example. Without moving your fingertip, you can move those joints all over the place. But the robot, you know, its main function is to do real useful work. And it maybe doesn't necessarily need all of those degrees of freedom right away. So we've stripped it down to a minimum sort of 28 fundamental degrees of freedom, and then, of course, our hands in addition to that. Humans are also pretty efficient at some things and not so efficient in other times. So, for example, we can eat a small amount of food to sustain ourselves for several hours. That's great. But when we're just kind of sitting around, no offense, but we're kind of inefficient. We're just sort of burning energy. So on the robot platform, what we're going to do is we're going to minimize that idle power consumption, drop it as low as possible. And that way we can just flip a switch and immediately the robot turns into something that does useful work. So let's talk about this latest generation in some detail, shall we? So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue our electrical system. So now that we have our sort of human-based research, and we have our first development platform, we have both research and execution to draw from for this design. Again, we're using that vehicle design foundation, so we're taking it from concept through design and analysis, and then build and validation. Along the way, we're going to optimize for things like cost and efficiency because those are critical metrics to take this product to scale eventually. How are we going to do that? Well, we're going to reduce our part count and our power consumption of every element possible. We're going to do things like reduce the sensing and the wiring at our extremities. You can imagine a lot of mass in your hands and feet is going to be quite difficult and power consumptive to move around. And we're going to centralize both our power distribution and our compute to the physical center of the platform. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So that means everything from sensing to fusing, charge management, and power distribution is all in one place. We're also leveraging both our vehicle products and our energy products to roll all of those key features into this battery. So that's streamlined manufacturing, really efficient and simple cooling methods, battery management, and also safety. And of course, we can leverage Tesla's existing infrastructure and supply chain to make it. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So as you know, Tesla already ships full self-driving computers in every vehicle we produce. We want to leverage both the autopilot hardware and the software for the humanoid platform, but because it's different in requirements and in form factor, we're going to change a few things first. So we still are it's going to do everything that a human brain does, processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well.
I told you we were going to get geeky, and we got geeky. Really, I just need this robot to do simple household things like vacuum, mop, clean the bathrooms, do some yard work. I'm not even opposed to helping it. Just an extra hand would be great. Like I vacuum the floors, Tesla Bot mops the floors. We'd be in good shape. We'd be a good team. The actuators that she's talking about, these are all the actuators that you would find typically at the joints to get the robot to actually move and twist and bend and things like that. The electrical system, like she said, is in the torso. One of the things that you didn't see was she popped up a slide, and it says that the brain is equipped with one Tesla system on a chip. So it's kind of like the little computer part there. Then it has Wi-Fi, LTE. I'd imagine by the time this thing gets released, it'd probably be 5G, but who knows? It has audio, so it can talk to you if you want it to. And it has security and safety features that they didn't really go into. All right, we're going to time warp a bit here. I skipped a bunch of information simply because I didn't think that it added anything to the show. But I will say that Tesla said that they have the ability to run computer simulations of crash tests. So they put up a video and it shows a front-end crash test with what looks like a Model 3. Tesla says the vehicle being tested has every part in simulation that actually goes on the car modeled, all the way down to the washers and spot welds. So when the vehicle crashes into that virtual barrier, they're able to see where the weaknesses in the vehicle are and, basically design a safer vehicle, which is what we all want. They can also take this same software and apply that to the Tesla Bot and determine potential damage if the Tesla Bot falls over, or, if there's any sort of other repetitive stresses on the robot itself. Like I'd imagine, just like with humans, the robot's going to need, there's going to be more wear on the actuators at the hip and at the knee than there would be like at the neck. I don't know if the Tesla Bot can turn its neck one way or the other, but if it could, the knees and the hips on Tesla Bot, those actuators are going to get stressed more than the ones that, don't do as much work, for instance. And they're able to, play that all out in the computer simulation with the overall goal of improving mobility of the robot, but also improving the durability of the robot. You don't want to spend $20,000 on a robot and have to replace actuators every year. All right, real soon we're going to jump into our next clip, but before we do that, I do need to say that they're going to put up a slide, and it shows on one side it says powertrain, which basically means the car, and on the other side it says robot. And under powertrain, it says 0 to 60 miles per hour, 50 to 80 miles per hour, city driving, highway driving, and racetrack driving. Those are all car related, and they use the software to make those experiences better, right? On the robot side of the slide, it says 28 actuators. So in this case, they have rotary or linear actuators. A rotary actuator would be like your hip or your shoulder or something like that. A linear would be more like your knee. And actually, they show this really cool video of one linear actuator picking up and setting down a 9-foot grand piano without any issue at all. It's just picking it up and setting it down. So these actuators are built. They're very durable and they're very strong. The actions that a robot's going to do is going to be forward walking on stairs, working with an object, squatting, squat walking, squat to pick up an object, turning or making a turn while walking, or turning while holding an object, stepping to the side, walking up a slope or down a slope, stepping to the side with an object, turning while walking, sliding an object in front of the torso parallel to ground access, so that, just like maybe you're handing it from the robot to a person or robot to robot, or setting it on a shelf. You're going to lift an object up with one arm, lift an object from the ground to straight eye, so right out in front of you. forward and backward push, and sideways push. So these are all the things the actuators need to do for the Tesla robot. So let's go ahead and listen to that clip now that I've explained the video that they're going to talk about.
So I would like to talk to you about the design process and the actuator portfolio in our robot. So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. We are carrying over most of our designing experience from the car to the robot. So in the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. Therefore, we use our model that generates the torque speed trajectories for our joints, which subsequently is going to be fed in our optimization model to run through the optimization process.
So again, this is all done through software to improve the Tesla robot. And I don't remember if they mentioned it in one of the clips I'm going to provide for you, but what they had said was that through this software, they were actually able to get Tesla robot to where it is much faster than they would have if they had not used the software itself. So they're very high on this simulation / modeling software that they're using. In our next clip, we're going to hear about Tesla Bot's hands. Now, I don't know anything about robotics or engineering or anything like that, but I will say it seems like to the layperson, which is me, that getting those hands to work like human hands has to be one of the hardest things to solve. Like getting the Tesla Bot to walk is not an easy thing to solve for sure, but the hands itself, like grabbing fine things like silverware or something small and delicate and doing these delicate tasks, that's got to be very difficult to solve. So I'm excited to see going forward how they get this done, because I think it's not going to be easy. So let's go ahead and listen to that clip.
The human hand has the ability to move at 300 degrees per second. It has tens of thousands of tactile sensors. And it has the ability to grasp and manipulate almost every object in our daily lives. For our robotic hand design, we were inspired by biology. We have 5 fingers and an opposable thumb. Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. So why a human-like robotic hand? Well, the main reason is that our factories and the world around us is designed to be ergonomic. So what that means is that it ensures that objects in our factory are graspable, but it also ensures that new objects that we may have never seen before can be grasped by the human hand and by our robotic hand as well. The converse there is pretty interesting because it's saying that these objects are designed to our hand instead of having to make changes to our hand to accompany a new object. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback. Sensor feedback is really important to learn a little bit more about the objects that we're grasping, and also for proprioception. And that's the ability for us to recognize where our hand is in space. One of the important aspects of our hand is that it's adaptive. This adaptability is involved essentially as complex mechanisms that allow the hand to adapt to the objects that's being grasped. Another important part is that we have a non-back drivable finger drive. This clutching mechanism allows us to hold and transport objects without having to turn on the hand motors.
Just based on that clip alone, how many of you think that making the hands actually work is easy? Because that doesn't sound easy to me. That sounds so hard. Let's go ahead and move into our next clip, which is all about software and taking the software that they were using for Tesla vehicles and just kind of converting that to something that's useful for the robot.
All right. So all those cool things we've shown earlier in the video were possible just in a matter of a few months, thanks to the amazing work that we've done on Autopilot over the past few years. Most of those components ported quite easily over to the bots environment. If you think about it, we're just moving from a robot on wheels to a robot on legs. So some of the components are pretty similar, and some other require more heavy lifting. So for example, our computer vision neural networks were ported directly from Autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the Autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. Another interesting problem to think about is, in indoor environments, mostly with absence of GPS signal, how do you get the bot to navigate to its destination? Say, for instance, to find its nearest charging station. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking.
So I'm not entirely convinced that it's that easy to convert what they're doing with the car onto a bipedal robot. I mean, again, I'm not an engineer, so I don't know. But one of the things that they showed was the evolution of this robot walking. It started off slow, but eventually became to, walk at a normal pace. And at some point in time, it didn't swing its arms at all. And then about halfway through, the robot started swinging its arms and it started looking more natural. It was slow to start, but, eventually got to where it needed to be, which was pretty neat. But walking is difficult. It's complex even for humans. I mean, we have all been there, whether you have been there yourself or you've watched somebody else that was there, when someone has had too much to drink, talking about an alcoholic drink, and they have a hard time standing up, and it's an even more difficult time walking. It's not something that most of us need to think about on a day-to-day basis. However, if you ever look at a toddler trying to walk, there's a lot going on there in terms of how they start off with their gait and how they eventually learn it. Folks who have lost the ability to walk and have had to go through therapy to learn how to walk again, it's a lot. Back to training a robot to walk, the robot needs to have, physical self-awareness. They need to know where they are in the space that they're in. So if they're walking down the middle of a hallway, there's probably not anything that they're going to slip on. But if they're too far to the right or too far to the left, they might run into a nice little table or a dresser or something. I don't know what you have in your hallways, but there might be something on the side of the wall that they would run into. The robot needs to be aware that those things exist. They need to be aware that there might be kids' toys on the ground, which causes a tripping hazard if you've ever had kids and they put their toys on the ground or on the stairs, for instance. So the robot needs to have a physical self-awareness. It also needs to have an energy-efficient gait. So if you've ever seen me run, I do not have an energy-efficient gait. When I run, I probably have too much of an energy-efficient gait when I walk, according to my wife. The robot needs to have balance, and they need to have coordinated motion, which I'm going to be honest, I do struggle with coordinated motion when I walk. I'm pretty clumsy. Now, I told you all that stuff so we can listen to our next clip. So let's dive in.
Hi everyone, I'm Felix. I'm a robotics engineer on the project, and I'm going to talk about walking. Walking seems easy, right? People do it every day. You don't even have to think about it. But there are some aspects of walking which are challenging from an engineering perspective. For example, physical self-awareness. That means having a good representation of yourself. What is the length of your limbs? What is the mass of your limbs? What is the size of your feet? All that matters. Also, having an energy-efficient gait. You can imagine there's different styles of walking, and all of them are equally efficient. Most important, keep balance, don't fall. And of course, also coordinate the motion of all of your limbs together. So now, humans do all of this naturally, but as engineers or roboticists, we have to think about these problems. And therefore, I'm going to show you how we address them in our locomotion planning and control stack. So we start with locomotion planning and our representation of the bot. That means a model of the robot's kinematics, dynamics, and the contact properties. And using that model and the desired path for the bot, our locomotion planner generates reference trajectories for the entire system. This means feasible trajectories with respect to the assumptions of our model. The planner currently works in 3 stages. It starts planning footsteps and ends with the entire motion for the system. And let's dive a little bit deeper in how this works. So in this video, we see footsteps being planned over a planning horizon, following the desired path. And we start from this and add then foot trajectories that connect these footsteps using toe-off and heel strike, just as humans do. And this gives us a larger stride and less knee bend for high efficiency of the system.
The clip goes on, and the engineer on stage, I think his name was Felix, he shows how they use the software to help the robot walk and improve without risking the robot falling down in real life. So it's okay if it falls down in a virtual world. We just don't want it falling down in real life. They showed an example of the real robot trying to walk before it was trained, and they had a tether on it. It would basically take a step, and then the tether had to save it because it would just fall down. Like, it was that quick. So pretty dramatic change over just a few months. Let's go ahead and jump into our next clip.
Hello, everyone. My name is Anand, and I'm going to talk to you about controls. So let's take the motion plan that Felix just talked about and put it in the real world on a real robot. Let's see what happens. It takes a couple steps and falls down. Well, that's a little disappointing. But we are missing a few key pieces here, which will make it walk. Now, as Felix mentioned, the motion planner is using an idealized version of itself and a version of reality around it. This is not exactly correct. It also expresses its intention through trajectories and wrenches. Wrenches are forces and torques that it wants to exert on the world to locomote. Reality is way more complex than any sim or model. Also, the robot is not simplified. It's got vibrations and modes, compliance, sensor noise, and on and on and on. So what does that do to the real world when you put the bot in the real world? Well, the unexpected forces cause unmodeled dynamics, which essentially the planner doesn't know about, and that causes destabilization, especially for a system that is dynamically stable like biped locomotion. So what can we do about it? Well, we measure reality. We use sensors and our understanding of the world to do state estimation. And state estimation, here you can see the attitude and pelvis pose, which is essentially the vestibular system in a human, along with the center of mass trajectory being tracked when the robot's walking in the office environment. Now we have all the pieces we need in order to close the loop. So we use our better bot model, we use the understanding of reality that we've gained through state estimation, and we compare what we want versus what we expect that reality is doing to us in order to add corrections to the behavior of the robot. Here, the robot certainly doesn't appreciate being poked, but it does an admirable job of staying upright. The final point here is a robot that walks is not enough. We need it to use its hands and arms to be useful. Let's talk about manipulation.
Let's talk about manipulation. I'm just going to summarize the next little part of this video to save time. In order to manipulate objects, what Tesla did was they used a human and they captured the motion of that human performing several tasks, but in this case, we're just going to use one task, and that is picking up a box from a middle shelf, and that's it. So the movement from the human, from the motion capture, is mapped onto the Tesla bot. The problem is that that's just one function. What happens if the Tesla bot can't get into a perfect position to get this box off? Or what happens if the Tesla bot needs to get it from the lower shelf onto the top shelf? That's like the human only did one motion. You can't have the human do literally millions of motions and then map that onto Tesla bot. It's just not very effective. Well, Tesla uses a function in the software called Optimizer. So the basic move of picking up the box from the middle shelf can be added to the software, and the software can figure out, hey, there's a box on the bottom shelf, so I'm just going to squat a little bit deeper and pick that box up from the bottom shelf, even though I'm only trained to do it on, I've only been trained to this point to do it on the middle shelf. Like the optimizer helps figure that out. Or if the Tesla bot isn't directly in front of the box, or it's off center a little bit for whatever reason, or the Tesla bot isn't facing the box, maybe there's a small amount of room or whatever. The optimizer in the software allows for the Tesla bot to overcome those weird kind of situations that don't happen all the time, but they are going to happen. So that's what the optimizer is doing. And again, it's way more efficient than having a human do this over and over and over again. They talked about what's next for Tesla bot. Well, they're going to start testing in one of Tesla's factories in a few months. I'm sure it's just going to be a very simple test. And my guess is, and I wrote this down before Elon said anything at the end of the show, but my guess is that it's going to be 5 years before consumers see this product and 3 years for factories. Now, at the end of the show, Elon says that he thinks 3 to 5 years before you can buy one. But I really think that the consumer, I don't think it's going to be consumer ready for 5 years, maybe 3 years for certain specific tasks in a factory. All right, that includes our Tesla bot portion of the show. Let's go ahead and jump into the FSD beta section of the show. Our first clip for this section is really for the engineers out there. This is for the nerdiest of the nerdy. So they're going to throw up a couple of slides, and the first one's going to say 2021. And for FSD beta, they had 2,000 beta customers. Between 2021 and 2022, they've had 35 software update releases, 281 models shipped. Don't exactly know what that means, I'm going to be honest. 18,659 pull requests, 75,778 models trained, and 4.8 million clip data set. I don't know what those things are. In 2022, we went from 2,000 beta customers to over 160,000 FSD beta testers. So pretty impressive. They're also going to throw up another slide. And in the middle, it says neural networks, and that there's a block that says neural networks. And in that block, you have occupancy and lanes and objects. Okay. You have that block neural networks, you have some things all the way around it. Just below neural networks, you have training data, which is its own block. Inside training data, you have auto labeling, simulation, and data engine. The training data flows into the neural network, okay, which again is occupancy and lane objects. That data then goes up again to planning. So it goes from the training data to neural networks and then to planning. But on the sides of neural networks, we have training infrastructure, or training infra is what they say in the video. So that's on the left side. That's going into the neural network. And we're going to learn what all these things are. And on the right side, we have AI compiler, and interface. And that's also feeding into the neural network. This is all going to make more sense once they start describing these things. But you need to know kind of in your head what this looks like. So let's go ahead and listen to the clip.
Hi, I'm Ashok. I lead the autopilot team alongside Milan. God, it's going to be so hard to top that Optimus section. We'll try nonetheless. Anyway, every Tesla that has been built over the last several years, we think has the hardware to make the car drive itself. We have been working on the software to add higher and higher levels of autonomy. This time around last year, we had roughly 2,000 cars driving our FSD beta software.
Since then, we have significantly improved the software's robustness and capability that we have now shipped it to 160,000 customers as of today. Thank you. This did not come for free. It came from the sweat and blood of the engineering team over the last 1 year. For example, we trained 75,000 neural network models just last 1 year. That's roughly a model every 8 minutes. That's coming out of the team, and then we evaluate them on our large clusters, and then we ship 281 of those models that actually improve the performance of the car. And this pace of innovation is happening throughout the stack. The planning software, the infrastructure, the tools, even hiring, everything is progressing to the next level. The FSD Beta software is quite capable of driving the car. It should be able to navigate from parking lot to parking lot, handling city street driving, stopping for traffic lights and stop signs, negotiating with objects at intersections, making turns, and so on. All of this comes from the camera streams that go through our neural networks that run on the car itself. It's not coming back to the server or anything. It runs on the car and produces all the outputs to form the world model around the car, and the planning software drives the car based on that. Today, we'll go into a lot of the components that make up the system. The occupancy network acts as the base geometry layer of the system. This is a multi-camera video neural network that from the images predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, balls, what have you, it predicts, if it's physically present, it predicts them, along with their future motion. On top of this base level of geometry, we have more semantic layers. In order to navigate the roadways, we need the lanes, of course. But then the roadways have lots of different lanes, and they connect in all kinds of ways. So it's actually a really difficult problem for typical computer vision techniques to predict the set of lanes and their connectivities. So we reached all the way into language technologies, and then pulled the state of the art from other domains, and not just computer vision, to make this task possible. For vehicles, we need their full kinematic state to control for them. All of this directly comes from neural networks. Video streams, raw video streams, come into the networks, go through a lot of processing, and then outputs the full kinematic state. The positions, velocities, acceleration, jerk, all of that directly comes out of the networks with minimal post-processing. That's really fascinating to me, because how is this even possible? What world do we live in that this magic is possible, that these networks predicts fourth derivatives of these positions, when people thought we couldn't even detect these objects? My opinion is that it did not come for free. It required tons of data, so we had to build sophisticated auto-labeling systems that churn through raw sensor data, run a ton of offline compute on the servers. It can take a few hours, run expensive neural networks, distill the information into labels that train our in-car neural networks. On top of this, we also use our simulation system to synthetically create images. And since it's a simulation, we trivially have all the labels. All of this goes through a well-oiled data engine pipeline, where we first train a baseline model with some data, ship it to the car, see what the failures are. And once we know the failures, we mine the fleet for the cases where it fails, provide the correct labels, and add the data to the training set. This process systematically fixes the issues. And we do this for every task that runs in the car.
Yeah, and to train these new massive neural networks, this year we expanded our training infrastructure by roughly 40 to 50%. So that sits us at about 14,000 GPUs today across multiple training clusters in the United States. We also worked on our AI compiler, which now supports new operations needed by those neural networks, and mapped them to the best of our underlying hardware resources. And our inference engine today is capable of distributing the execution of a single neural network across two independent systems on chips, essentially two independent computers interconnected within the same full self-driving computer. And to make this possible, we had to keep a tight control on the end-to-end latency of this new system. So we deployed more advanced scheduling code across the full FSD platform.
All of these neural networks running in the car together produce the vector space, which is again the model of the world around the robot or the car. And then the planning system operates on top of this, coming up with trajectories that avoid collisions or smooth, make progress towards the destination using a combination of model-based optimization plus neural network that helps optimize it to be really fast.
All right, just to recap real quick, the occupancy part of the neural network, those are models of the physical world that's around the car, and it determines if something occupies a space or it doesn't. It can even determine if there's something, if an object is there, if it's partially occluded. And we're going to talk more about lanes and objects later, as well as the auto labeling and simulation and stuff like that. I just kind of want to get some things out here real quick. In terms of the neural network block, in terms of training data, or excuse me, training infrastructure, this applies to both cars and the Tesla bots. The Tesla cars have lanes that they got to stay in, of course, and the Tesla bots would have paths. Our next clip, we're going to learn more about the planning section of the neural network. But before we get to the clip, I got to explain something to you. The video that they're going to show, it shows an intersection with multiple lanes, lots of traffic. A pedestrian is walking across the street outside of a crosswalk, and the car, the Tesla car, needs to make a left turn, but the pedestrian is still crossing the intersection. Like I said, on the left side. So the car has a couple options. The car can run over the pedestrian. It can turn in front of the pedestrian, or the car can nose out into the intersection, wait for the pedestrian to safely pass like any normal person would, and then the Tesla can pull forward safely around the pedestrian and continue traveling along their merry way. So that's the clip they're going to talk about in the planning sections. Let's go ahead and jump in and listen.
Hi all, I'm Paril Jain. Let's use this intersection scenario to dive straight into how we do the planning and decision making in Autopilot. So we are approaching this intersection from a side street, and we have to yield to all the crossing vehicles. Right as we are about to enter the intersection, the pedestrian on the other side of the intersection decides to cross the road without a crosswalk. Now, we need to yield to this pedestrian, yield to the vehicles from the right, and also understand the relation between the pedestrian and the vehicle on the other side of the intersection. So a lot of these intra-object dependencies that we need to resolve in a quick glance. And humans are really good at this. We look at a scene, understand all the possible interactions, evaluate the most promising ones, and generally end up choosing a reasonable one. So let's look at a few of these interactions that Autopilot system evaluated. We could have gone in front of this pedestrian with a very aggressive longitudinal lateral profile. Now, obviously, we are being a jerk to the pedestrian, and we would spook the pedestrian and his cute pet. We could have moved forward slowly, shot for a gap between the pedestrian and the vehicle from the right. Again, we are being a jerk to the vehicle coming from the right, but you should not outright reject this interaction in case this is only safe interaction available. Lastly, the interaction we ended up choosing: stay slow initially, find the reasonable gap, and then finish the maneuver after all the agents pass. Now, evaluation of all of these interactions is not trivial, especially when you care about modeling the higher order derivatives for other agents. For example, what is the longitudinal jerk required by the vehicle coming from the right when you assert in front of it? Relying purely on collision checks with marginal predictions will only get you so far, because you will miss out on a lot of valid interactions. This basically boils down to solving a multi-agent joint trajectory planning problem over the trajectories of ego and all the other agents. Now, how much ever you optimize, there's going to be a limit to how fast you can run this optimization problem. It will be close to order of 10 milliseconds, even after a lot of incremental approximations. Now, for a typical crowded, unprotected lift, say you have more than 20 objects, each object having multiple different future modes, the number of relevant interaction combinations will blow up.
We as humans have a tendency to think that things are easier than they are. And the more I listen to this presentation, the more I appreciate what Tesla's doing and other companies like Tesla are doing in terms of the full self-driving. There are so many things that have to be considered and thought about. Otherwise, it would just be catastrophic if these things were just running wild and not making good decisions. So I'm glad that they are. The next, we're going to hear about the training infrastructure. So let's go ahead and jump into that clip.
Let's talk about some training infrastructure. So we've seen a couple of videos, 4 or 5. I think and care more and worry more about a lot more clips than that. So we've been looking at the occupancy networks just from Phil. Just Phil's videos, it takes 1.4 billion frames to train that network, what you just saw. And if you have 100,000 GPUs, it would take 1 hour. But if you have one GPU, it would take 100,000 hours. So that is not a humane time period that you can wait for your training job to run, right? We want to ship faster than that. So that means you're going to need to go parallel. So you need more compute for that. That means you're going to need a supercomputer. So this is why we've built in-house 3 supercomputers comprising of 14,000 GPUs, where we use 10,000 GPUs for training and around 4,000 GPUs for auto-labeling. All these videos are stored in 30 petabytes of a distributed, managed video cache. You shouldn't think of our data sets as fixed, let's say, as you think of your ImageNet or something, with like 1 million frames. You should think of it as a very fluid thing. So we've got 500,000 of these videos flowing in and out of these clusters every single day. And we track 400,000 of these kind of Python video instantiations every second. So that's a lot of calls. We're going to need to capture that in order to govern the retention policies of this distributed video cache. So underlying all of this is a huge amount of infra, all of which we build and manage in-house. So you cannot just buy 14,000 GPUs and then 30 petabytes of flash NVMe and just put it together and let's go train. It actually takes a lot of work, and I'm going to go into a little bit of that. What you actually typically want to do is you want to take your accelerator, so that could be the GPU or Dojo, which we'll talk about later, and because that's the most expensive component, that's where you want to put your bottleneck. And so that means that every single part of your system is going to need to outperform this accelerator. And so that is really complicated. That means that your storage is going to need to have the size and the bandwidth to deliver all the data down into the nodes. These nodes need to have the right amount of CPU and memory capabilities to feed into your machine learning framework. This machine learning framework then needs to hand it off to your GPU, and then you can start training. But then you need to do so across hundreds or thousands of GPU in a reliable way, in lockstep, and in a way that's also fast. So you're also going to need an interconnect. Extremely complicated. We'll talk more about Dojo in a second. So first, I want to take you through some optimizations that we've done on our cluster. So we're getting in a lot of videos, and video is very much unlike, let's say, training on images or text, which I think is very well established. Video is quite literally a dimension more complicated. And so that's why we needed to go end-to-end from the storage layer down to the accelerator and optimize every single piece of that. Because we train on the photon count videos that come directly from our fleet, we train on those directly. We do not post-process those at all. The way it's just done is we seek exactly to the frames we select for our batch. We load those in, including the frames that they depend on. So these are your iframes or your key frames. We package those up, move them into shared memory, move them into a double buffer on the GPU, and then use the hardware decoder that's on the accelerator to actually decode the video. So we do that on the GPU natively. And this is all in a very nice PyTorch extension. Doing so unlocked more than 30% training speed increase for the occupancy networks and freed up basically the whole CPU to do any other thing.
That is a lot, friends. That is a lot. That is pretty impressive. I want to just go ahead and reiterate 1.4 billion frames from the occupancy network gets fed into the training infrastructure. That's insane. Also, they said that it would take 100,000 GPUs 1 hour to train the network with this much data. It would take one GPU 100,000 hours. And I just wanted to break down what 100,000 hours looks like. 100,000 hours is 4,166 days, or 11 and a half years. So Tesla's going to talk a little bit more about how they're able to, be a little faster with their system when they get to Dojo, which is pretty close to release. But before we get to Dojo, we are going to talk about lane prediction in our next clip. And they popped up a picture of a intersection. And this is an intersection that you might find in a European country. I've not seen any intersections like this here in the United States, but I have seen some in different countries, and I'm always confused by them. But this is like a, let's see, 1, 2, 3, 4, 5, a 6-lane intersection. It's not abundantly clear to me what's going on in this intersection. It's very complicated. I would most likely fail and make a lot of people angry just trying to navigate this intersection. I don't know how the car is going to do it. So when they're talking in the next clip, I want you to keep this big picture in your head. Okay? So let's go ahead and jump into it.
Hi, everybody. My name is John Emmons. I lead the Autopilot Vision team. I'm going to cover 2 topics with you today. The first is how we predict lanes, and the second is how we predict the future behavior of other agents on the road. In the early days of Autopilot, we modeled the lane detection problem as an image space instance segmentation task. Our network was super simple, though. In fact, it was only capable of predicting lanes of a few different kinds of geometries. Specifically, it would segment the ego lane, it could segment adjacent lanes, and then it had some special casing for forks and merges. This simplistic modeling of the problem worked for highly structured roads like highways. But today we're trying to build a system that's capable of much more complex maneuvers. Specifically, we want to make left and right turns at intersections, where the road topology can be quite a bit more complex and diverse. When we try to apply this simplistic modeling of the problem here, it just totally breaks down. Taking a step back for a moment, what we're trying to do here is to predict the sparse set of lane instances and their connectivity. And what we want to do is to have a neural network that basically predicts this graph, where the nodes are the lane segments, and the edges encode the connectivities between these lanes. So what we have is our lane detection neural network. It's made up of 3 components. In the first component, we have a set of convolutional layers, attention layers, and other neural network layers that encode the video streams from our 8 cameras on the vehicle and produce a rich visual representation. We then enhance this visual representation with a coarse road-level map data, which we encode with a set of additional neural network layers that we call the lane guidance module. This map is not an HD map, but it provides a lot of useful hints about the topology of lanes inside of intersections, the lane counts on various roads, and a set of other attributes that help us. The first 2 components here produce a dense tensor that sort of encodes the world, but what we really want to do is to convert this dense tensor into a sparse set of lanes and their connectivities. We approach this problem like an image captioning task, where the input is this dense tensor, and the output text is predicted into a special language that we developed at Tesla for encoding lanes and their connectivities. In this language of lanes, the words and tokens are the lane positions in 3D space. In the ordering of the tokens, and predicted modifiers in the tokens encode the connective relationships between these lanes. By modeling the task as a language problem, we can capitalize on recent autoregressive architectures and techniques from the language community for handling the multimodality of the problem. We're not just solving the computer vision problem at Autopilot, we're also applying the state-of-the-art in language modeling and machine learning more generally.
All right, so it is much harder to apply full self-driving or Autopilot or any sort of driver assist technology, I guess, to surface streets than it is to highways. I mean, not the least of which is there's bikers, pedestrians and things like that on surface streets where you don't normally find that on a freeway. But also you have these, like he mentioned, these really complicated intersections where the car needs to know how to make a lot of, the car needs to know a lot of rules that I would guess that some humans don't even know of how to navigate, like I said, that 6-lane intersection. I wouldn't know how to navigate it. Like I said, I would just do basically what the car did in front of me. And then if I did it wrong, then I'd have to just figure it out. Miles down the road, I'd have to find a different route because I'm not going through that intersection again. One of the things that they talked about with the future behavior of other agents on the road, they used an example of someone who ran a red light and turned left and crossed into the lane or across the lane of their test car. The test car decided to yield to the red light runner instead of actually hitting the red light runner, which I think we can all agree that that's a positive outcome. Another thing that I thought was more interesting than that was there was a parked car in the lane, like on the right lane here in the United States. And it was maybe so someone could load or offload something. Instead of the test car just waiting for the car in front of it to move, the test car safely went around the parked car. And I don't know if I put this into, I don't know if I pulled this clip or not, but at the end of the presentation, one of the engineers, when she was speaking, she said that it's basically, there's like an argument that happens. Is this car going to move? Is it not going to move? Is it disabled? Is it not disabled? And the argument happens on the computer. It's not with the passenger or the driver of the vehicle, although that would be funny if the car was arguing with you. But there's a little argument that takes place, and then a decision is made as to what's the best action moving forward. So I thought that was pretty cool. I'm going to skip over the auto lane labeling section. I'm just going to give you a quick summary. Tesla has developed a new, faster, and much more efficient way of auto labeling. So the computer goes through and does 20 million functions of labeling a day. And then a human labeler is only used to confirm that the auto labeler labeled this properly. And to give you an idea why labeling is important, that's how in our previous example of the car parked on the side of the road where the person was either loading or offloading the car or was disabled, that labeling is used in that argument of whether or not the car should go around the disabled vehicle, the test car should go around the vehicle, or if it should just wait patiently. So that labeling might show it as a disabled vehicle. In reality, when a labeler goes in, like a human labeler goes in, they can see somebody like pulling a surfboard out and somebody else getting out. So they could label it as something different. I don't know what all their labels are, so I'm not going to tell you what they could have labeled it as. But it's not a disabled car. It's not a parked car. It's something different, and that's what the labeling does. And like I said, it's 20 million functions a day. And this auto labeling system, they said, was set up like a factory. So it's not just haphazardly like throwing information in and being labeled. Like there's a streamlined process, and they didn't really get into what that streamlined process was, but there's a streamlined factory-like process for this labeling software, and they are, quite happy with it. So that's pretty cool. The most interesting part of the presentation, or at least what I thought was the most interesting part of the presentation, was the simulation part. So we're going to go ahead and listen to that. He is going to start to explain in detail on how they create the cities inside the simulation. What you need to know is, as he takes you through this process, imagine the screen is completely dark. And then as he's talking about it, like the trees and the medians, those are being added as he's talking about them, the streets, the buildings, the vehicles, and then the final product. And this is all done with the help of the Unreal Engine, which is what we talked about previously. And one of the other cool things is you could have alterations. So you could have the same intersection, but they have, maybe you can say, I want really thick trees and vegetation in this area, and it will do that. Or you can say that I want different weather conditions, rain, fog, snow, that kind of thing. And it was kind of cool. They recreated San Francisco streets. Jeez. They recreated the San Francisco streets. It's a long night. They recreated San Francisco streets in 2 weeks, and the whole thing was done by one person. Now, they didn't recreate the entire city of San Francisco, just the streets, but still, that's pretty cool. So let's go ahead and listen to that clip.
Thank you, Yagen. My name is David, and I'm going to talk about simulation. So simulation plays a critical role in providing data that is difficult to source and/or hard to label. However, 3D scenes are notoriously slow to produce. Take, for example, the simulated scene playing behind me. A complex intersection from Market Street in San Francisco. It would take 2 weeks for artists to complete. And for us, that is painfully slow. However, I'm going to talk about using Yagen's automated ground truth labels along with some brand new tooling that allows us to procedurally generate this scene and many like it in just 5 minutes. That's an amazing 1,000 times faster than before. So let's dive in to how a scene like this is created. We start by piping the automated ground truth labels into our simulated world creator tooling inside the software Houdini. Starting with road boundary labels, we can generate a solid road mesh and retopologize it with the lane graph labels. This helps inform important road details like crossroad slope and detailed material blending. Next, we can use the line data and sweep geometry across its surface and project it to the road, creating lane paint decals. Next, using median edges, we can spawn island geometry and populate it with randomized foliage. This drastically changes the visibility of the scene. Now, the outside world can be generated through a series of randomized heuristics. Modular building generators create visual obstructions, while randomly placed objects like hydrants can change the color of the curbs, while trees can drop leaves below it, obscuring lines or edges. Next, we can bring in map data to inform positions of things like traffic lights or stop signs. We can trace along its normal to collect important information like number of lanes and even get accurate street names on the signs themselves. Next, using lane graph, we can determine lane connectivity and spawn directional road markings on the road and their accompanying road signs. And finally, with lane graph itself, we can determine lane adjacency and other useful metrics to spawn randomized traffic permutations inside our simulator. And again, this is all automatic, no artist in the loop, and happens within minutes. And now this sets us up to do some pretty cool things. Since everything is based on data and heuristics, we can start to fuzz parameters to create visual variations of the single ground truth. It can be as subtle as object placement and random material swapping to more drastic changes like entirely new biomes or locations of environment, like urban, suburban, or rural. This allows us to create infinite targeted permutations for specific ground truths that we need more ground truth for. And all this happens within a click of a button. And we can even take this one step further by altering our ground truth itself. Say John wants his network to pay more attention to directional road markings to better detect an upcoming captive left turn lane. We can start to procedurally alter our lane graph inside the simulator to help to create entirely new flows through this intersection to help focus the network's attention to the road markings to create more accurate predictions. And this is a great example of how this tooling allows us to create new data that could never be collected from the real world.
Like I said, it's really cool stuff. Like that part of the video is worth going back to watch just because it's so cool. Let's go ahead and jump into our next clip, which is how does all this make autopilot and full self-driving better?
Hi, everyone. My name is Kate Park, and I'm here to talk about the data engine, which is the process by which we improve our neural networks via data. We're going to show you how we deterministically solve interventions via data and walk you through the life of this particular clip. In this scenario, autopilot is approaching a turn and incorrectly predicts that crossing vehicle as stopped for traffic, and thus a vehicle that we would slow down for. In reality, there's nobody in the car. It's just awkwardly parked. We've built this tooling to identify the mispredictions, correct the label, and categorize this clip into an evaluation set. This particular clip happens to be one of 126 that we've diagnosed as challenging parked cars at turns. Because of this infra, we can curate this evaluation set without any engineering resources custom to this particular challenge case. To actually solve that challenge case requires mining thousands of examples like it, and it's something Tesla can trivially do. We simply use our data sourcing infra, request data, and use the tooling shown previously to correct the labels. By surgically targeting the mispredictions of the current model, we're only adding the most valuable examples to our training set. We surgically fix 13,900 clips, and because those were examples where the current model struggles, we don't even need to change the model architecture. A simple weight update with this new valuable data is enough to solve the challenge case. So you see, we no longer predict that crossing vehicle as stopped, as shown in orange, but parked, as shown in red. In academia, we often see that people keep data constant, but at Tesla, it's very much the opposite. We see time and again that data is one of the best, if not the most deterministic lever to solving these interventions. We just showed you the data engine loop for one challenge case, namely these parked cars at turns. But there are many challenge cases even for one signal of vehicle movement. We apply this data engine loop to every single challenge case we've diagnosed, whether it's buses, curvy roads, stopped vehicles, parking lots. And we don't just add data once, we do this again and again to perfect the semantic. In fact, this year, we updated our vehicle movement signal 5 times, and with every weight update trained on the new data, we push our vehicle movement accuracy up and up. This data engine framework applies to all our signals, whether they're 3D, multicam video, whether the data is human-labeled, auto-labeled, or simulated, whether it's an offline model or an online model. And Tesla's able to do this at scale because of the fleet advantage, the infra that our Eng team has built, and the labeling resources that feed our networks.
So it turns out that I did put that clip in there. What are you going to do? Hopefully she explained it way better than I explained it to you. Let's talk about Tesla Dojo. And before we get to the clip, it's going to be nerdy. So I think that the folks who listen to this show are nerdy enough to understand, but it's going to be a nerdy clip.
My name is Pete Bannon. I run the custom silicon and low voltage teams at Tesla.
And my name is Ganesh Venkat. I run the Dojo program.
Thank you. I'm frequently asked, why is a car company building a supercomputer for training? And this question fundamentally misunderstands the nature of Tesla. At its heart, Tesla is a hardcore technology company. All across the company, people are working hard in science and engineering to advance the fundamental understanding and methods that we have available to build cars, energy solutions, robots, and anything else that we can do to improve the human condition around the world. It's a super exciting thing to be a part of, and it's a privilege to run a very small piece of it in the semiconductor group. Tonight we're going to talk a little bit about Dojo and give you an update on what we've been able to do over the last year. But before we do that, I wanted to give a little bit of background on the initial design that we started a few years ago. When we got started, the goal was to provide a substantial improvement to the training latency for our autopilot team. Some of the largest neural networks they train today run for over a month, which inhibits their ability to rapidly explore alternatives and evaluate them. So, a 30x speed up would be really nice if we could provide it at a cost competitive and energy competitive way. To do that, we wanted to build a chip with a lot of arithmetic units that we could utilize at a very high efficiency. And we spent a lot of time studying whether we could do that using DRAM, various packaging ideas, all of which failed. And in the end, even though it felt like an unnatural act, we decided to reject DRAM as the primary storage medium for this system, and instead focus on SRAM embedded in the chip. SRAM provides, unfortunately, a modest amount of capacity, but extremely high bandwidth and very low latency, and that enables us to achieve high utilization with the arithmetic units. Those choices, that particular choice led to a whole bunch of other choices. For example, if you want to have virtual memory, you need page tables. They take up a lot of space. We didn't have space, so no virtual memory. We also don't have interrupts. The accelerator is a bare bones raw piece of hardware that's presented to a compiler, and the compiler is responsible for scheduling everything that happens in a deterministic way. So there's no need or even desire for interrupts in the system. We also chose to pursue model parallelism as a training methodology, which is not the typical situation. Most machines today use data parallelism, which consumes additional memory capacity, which we obviously don't have. So all of those choices led us to build a machine that is pretty radically different from what's available today. We also had a whole bunch of other goals. One of the most important ones was no limits. So we wanted to build a compute fabric that would scale in an unbounded way for the most part. I mean, obviously there's physical limits now and then, but pretty much if your model was too big for the computer, you just had to go buy a bigger computer. That's what we were looking for. Today, the way machines are packaged, there's a pretty fixed ratio of, for example, GPUs, CPUs, and DRAM capacity and network capacity. And we really wanted to disaggregate all that so that as models evolved, we could vary the ratios of those various elements and make the system more flexible to meet the needs of the autopilot team.
Yeah, and it's so true, Pete, like no limits philosophy was our guiding star all the way. All of our choices were centered around that. And to the point that we didn't want traditional data center infrastructure to limit our capacity to execute these programs at speed. So that's why we integrated vertically our data center, the entire data center. By doing a vertical integration of the data center, we could extract new levels of efficiency. We could optimize power delivery, cooling, and as well as system management across the whole data center stack, rather than doing box by box and integrating those boxes into data centers. And to do this, we also wanted to integrate early to figure out limits of scale for our software workloads. So we integrated Dojo environment into our autopilot software very early, and we learned a lot of lessons.
Okay, we're going to skip the next section, which is the Dojo hardware. And actually, I thought that was a very interesting section. It's just that it gets so detailed and so nerdy, and they relies heavily on the visuals. I didn't think it was beneficial for an audio program, so I went ahead and cut it. We've officially completed the full self-driving autopilot beta neural net section of the show, and we are now on to the question and answer section. And fortunately for you, I don't have a lot of comments after these questions and answers, so this should go fairly quickly. The first one is, why use a tendon-driven system for the hands? Specifically, the person asking the question was concerned because he thought that would actually, be less efficient and less durable. So let's listen to the answer.
Yeah. Hi. Thank you very much. I was impressed here. Yeah. I was impressed very much by Optimus, but I wonder why tendon-driven, the hand? Why did you choose a tendon-driven approach for the hand? Because tendons are not very durable. And why spring-loaded?
Yeah. Hello, is this working? Cool, awesome. Yes, that's a great question. When it comes to any type of actuation scheme, there's trade-offs between, whether or not it's a tendon-driven system or some type of linkage-based system.
Just keep the mic close to your mouth.
A little bit closer.
Yeah.
Hear me? Cool.
Yeah.
The main reason why we went for a tendon-based system is that, first we actually investigated some synthetic tendons, but we found that metallic Bowden cables are, a lot stronger. One of the advantages of these cables is that it's very good for part reduction. We do want to make a lot of these hands, so having a bunch of parts, a bunch of small linkages ends up being a problem when you're making a lot of something. One of the big reasons that tendons are better than linkages in a sense is that you can be anti-backlash. So anti-backlash essentially, allows you to not have any gaps or, stuttery motion in your fingers. Spring-loaded, mainly what spring-loaded allows us to do is allows us to have active opening. So instead of having to have two actuators to drive the fingers closed and then open, we have the ability to, have the tendon drive them closed and then the springs passively extend. And this is something that's seen in our hands as well, right? We have the ability to actively flex, and then we also have the ability to extend.
I mean, our goal with Optimus is to have a robot that is maximally useful as quickly as possible. So there's a lot of ways to solve the various problems of a humanoid robot. We're probably not barking up the right tree on all the technical solutions. And I should say that we're open to evolving the technical solutions that you see here over time. They're not locked in stone. But we have to pick something, and we want to pick something that's going to allow us to produce the robot as quickly as possible and have it, like I said, be useful as quickly as possible. We're trying to follow the goal of fastest path to a useful robot that can be made at volume. And we're going to test the robot internally at Tesla in our factory. And just see, like, how useful is it? Because you have to have you've got to close the loop on reality to confirm that the robot is, in fact, useful. So we're just going to use it to build things. And we're confident we can do that with the hand that we have currently designed. But for sure there'll be hand version 2, version 3, and we may change the architecture quite significantly over time.
So Elon has said over and over and over again that the world is built for humans. And one of the biggest mistakes he made with the production of Model 3 is he thought a lot of things could be done with a robot, when in reality, fine motor skills are kind of important. So, which, is why we have a Tesla bot that has 5 fingers and an opposable thumb. Over time, it makes sense that they're going to iterate not only on the hand, but all the other parts that go into the Tesla bot. So that makes sense. Let's go ahead and jump into our next clip, which is all about, are you going to give Tesla bot a personality?
The Optimus robot is really impressive. You did a great job. Bipedal robots are really difficult. But what I noticed might be missing from your plan is to acknowledge the utility of the human spirit, and I'm wondering if Optimus will ever get a personality and be able to laugh at our jokes while it folds our clothes.
Yeah, absolutely. I think we want to have really fun versions of Optimus, so that Optimus can both be utilitarian and do tasks, but can also be kind of like a friend and a buddy and hang out with you. And I'm sure people will think of all sorts of creative uses for this robot. The thing, once you have the core intelligence and actuators figured out, then you can actually, put all sorts of costumes, I guess, on the robot. I mean, you can make the robot look. You can skin the robot in many different ways, I'm sure people will find very interesting ways to versions of Optimus. So,
do you get the feeling that Elon has thought of an adult way, like specifically an adult way to use this robot? He mentions this a lot in a specific way. I'm sure people will find uses for it. No, wink, wink, nudge, nudge. So he's clearly thought about that. One of the things about giving the Tesla bot a personality that I think is great is this is going to help people who are shut-ins, or could potentially help people who are shut-ins who are just live alone and they can't get out of the house, and they need things done for them. Cooking and cleaning being one of those things, but some sort of interaction is also important. Kind of along these same lines, in Japan, Sony made these robot dogs, and I believe they're mostly like kind of as toys for kids. But what ended up happening is a lot of older folks in Japan This was their companion, this robot dog. It was a creature that they could interact with and feel less lonely. And in Japan, I don't know a lot about Japan, but I know it's hard to own a pet in some places in Japan. And so these robot dogs, you don't have to clean up after them, you don't have to feed them, but they still provide some, comfort to people who are older, which I think if TeslaBot could do that, in some people's eyes, it might be worth the price. Even if it does cost $20,000, it might be worth it to them. Our next clip is about the future of Dojo. Is Tesla going to license it out? Are they going to sell it as a software package? What may the future hold for Dojo?
I see today you have very attractive product with Dojo and its applications. So I'm wondering what's the future for the Dojo platform? Will you provide infrastructure as service like AWS, or you will sell the chip like the NVIDIA? So basically, what's the future? Because I see you use 7 nanometer, so the development cost is easily over $10 million US. How do you make the business business wise?
Yeah, Dojo is a very big computer, and actually will use a lot of power and needs a lot of cooling. So I think it's probably going to make more sense to have Dojo operate in a Amazon Web Services manner than to try to sell it to someone else. So that would be the most efficient way to operate Dojo, is just have it be a service that you can use that's available online, and that where you can train your models way faster and for less money. And as the world transitions to software 2.0,
and that's on the bingo card.
As someone I know has to know to drink 5 tequilas. Let's see. Software 2.0
yeah.
will use a lot of neural net training. So, it kind of makes sense that over time, as there's more neural net stuff, people will want to use the fastest, lowest cost neural net training system. So I think there's a lot of opportunity in that direction.
The someone that Elon knows that had to drink 5 tequila shots was Andrej Karpathy, who was the former head of Tesla Autopilot, or was it AI? Anyway, he used to work there. He doesn't work there anymore. But apparently they keep saying software 2.0 because someone told Andre that he had to take a shot every time it was said. So that's why Elon said it so many times. Amazon Web Services for a service like this makes sense to me. I don't know that anybody needs to, download Dojo to their computer. It makes sense because it requires a lot of hardware, and I know I skipped that part, but it requires a lot of hardware to run Dojo. So to have something that's like an Amazon Web Services type thing where people just kind of lease Dojo in the cloud, I think that makes a lot of sense. Our next question is about AI safety.
Hi. So at the beginning, Elon said that Tesla was potentially interested in building artificial general intelligence systems. Given the potentially transformative impact of a technology like that, it seems prudent to invest in technical AGI safety expertise specifically. I know Tesla does a lot of technical narrow AI safety research. I was curious if Tesla was intending to try to build expertise in technical artificial general intelligence safety specifically.
Well, if it starts looking like we're going to be making a significant contribution to artificial general intelligence, then we'll for sure invest in safety. I'm a big believer in AI safety. I think there should be an AI sort of regulatory authority at the government level, just as there is a regulatory authority for anything that affects public safety. So we have a regulatory authority for aircraft and cars and sort of food and drugs. And because they affect public safety, and AI also affects public safety. So I think, and this is not really something that government I think understands yet, but I think there should be a referee that is ensuring or trying to ensure public safety for AGI. And if you think of like, what are the elements that are necessary to create AGI? Like the accessible data set is extremely important, and if you've got a large number of cars and humanoid robots processing, petabytes of video data and audio data from the real world, just like humans, that might be the biggest data set. It probably is the biggest data set. Because in addition to that, you can obviously incrementally scan the internet. But what the internet can't quite do is have millions or hundreds of millions of cameras in the real world, and with like I said, with audio and other sensors as well. So I think we probably will have the most amount of data, and probably the most amount of training power. Therefore, probably we will make a contribution to AGI.
I don't have a whole lot more to say here. AGI is advanced general intelligence, so it's kind of like the overall knowledge base for artificial intelligence. I don't know a whole lot about it. I only know a very small amount, so I don't want to say too much because I'll sound dumber than I already do. But I don't have anything else really to add on, the safety component of AI safety. Let's go ahead and jump into our next clip, which is about expanding full self-driving beta to other countries.
Hi, I want to switch the gear to the autopilot. So when you guys plan to roll out the FSD beta to countries other than US and Canada? And also my next question is, what's the biggest bottleneck or the technological barrier you think in the current autopilot stack? And how you envision to solve that to make the autopilot is considerably better than human in terms of like performance matrix, like safety assurance and the human confidence? And I think you also mentioned for FSD V11, you are guys going to combine the highway and the city as a single stack and some architectural big improvement. Can you maybe expand a bit on that? Thank you.
Well, that's a whole bunch of questions. Well, we're hopeful to be able to. I think from a technical standpoint, FSD beta should be possible to roll out FSD beta worldwide by the end of this year. But for a lot of countries, we need regulatory approval, and so we are somewhat gated by the regulatory approval in other countries. But I think from a technical standpoint, it will be ready to go to a worldwide beta by the end of this year. And there's quite a big improvement that we're expecting to release next month. That will be especially good at assessing the velocity of fast-moving cross-traffic and a bunch of other things. So, anyone want to elaborate?
Yeah, I guess so. There used to be a lot of differences between production autopilot and the full self-driving beta, but those differences have been getting smaller and smaller over time. I think just a few months ago, we now use the same vision-only object detection stack in both FSD and in the production autopilot on all vehicles. There's still a few differences, the primary one being the way that we predict lanes right now. So we upgraded the modeling of lanes so that it could handle these more complex geometries like I mentioned in the talk. In production autopilot, we still use a simpler lane model, but we're extending our current FSD beta models to work in all sort of highway scenarios as well.
And the version of FSD beta that I drive actually does have the integrated stack. So it uses the FSD stack both in city streets and highway, and it works quite well for me. But we need to validate it in all kinds of weather, like heavy rain, snow, dust, and just make sure it's working as better than the production stack across a wide range of environments. But we're pretty close to that. I think it's, I don't know, maybe it'll definitely be before the end of the year, and maybe November.
Yeah, in our personal drives, the FSD stack on highway drives already way better than the production stack we have. And we do expect to also include the parking lot stack as a part of the FSD stack before the end of this year. So that will basically bring us to, you sit in the car in the parking lot and drive till the end of the parking lot at a parking spot before the end of this year.
Yeah, and in terms of the fundamental metric to optimize against is how many miles between a necessary intervention. So just massively improving how many miles the car can drive in full autonomy before an intervention is required that is safety critical. So yeah, that's the fundamental metric that we're measuring every week, and we're making radical improvements on that.
Okay, so two things here. One is the biggest hurdle for expanding full self-driving to other countries is regulatory approval. He gives some great examples and some great information here, so I'm not going to go through that. But I will say, beware of Elon's timelines. They're not often right. They're often optimistic. We'll jump into our next clip, which is, will there be a Tesla factory completely run by Tesla bots, and when will it be available?
Hi, Elon. You are actually bringing the humanity to the next level. Literally, Tesla and you are bringing the humanity to the next level. So you said Optimus Prime, Optimus will be used in next Tesla factory. My question is, will a new Tesla factory will be fully run by Optimus program? And when can general public order a humanoid?
Yeah, I think it'll we're going to start Optimus with very simple tasks in the factory. Like maybe just like loading a part, like you saw in the video, loading a part, carrying a part from one place to another, or loading a part into one of our more conventional robot cells that welds the body together. So we'll start, just trying to, how do we make it useful at all? And then gradually expand the number of situations where it's useful. And I think that the number of situations where Optimus is useful will grow exponentially, like really, really fast. In terms of when people can order one, I don't know. I think it's not that far away. Well, I think you mean when can people receive one? So I don't know. I'd say probably within 3 years, and not more than 5 years. Within 3 to 5 years, you could probably receive an Optimus.
And I go back to maybe 3 years for commercial, 5 years for, just having a personal Optimus at your house. Our next clip is, should Tesla open source some or all of TeslaBot? I think Elon gave a really good answer here, so let's go ahead and listen to that.
I feel the best way to make the progress for AGI is to involve as many smart people across the world as possible. And given the size and resource of Tesla compared to robot companies, and given the state of humanoid research at the moment, would it make sense for the kind of Tesla to sort of open source some of the simulation hardware parts? I think Tesla can still be the dominant platformer where it can be something like Android OS or like iOS stuff for the entire humanoid research. Would that be something that, rather than keeping the Optimus to just Tesla researchers or the factory itself, can you open it and let the whole world explore humanoid research?
I think we have to be careful about Optimus being potentially used in ways that are bad, because that is one of the possible things to do. So I think we'd provide Optimus where you can provide instructions to Optimus, but where those instructions are, governed by some laws of robotics that you cannot overcome. So, not doing harm to others, and you would have, I think, probably quite a few safety-related things with Optimus. Yeah.
Yeah, I am convinced that AI is not going to evolve and want to kill us. I don't think that's going to happen. I don't think it's going to evolve on its own and become sentient and be like, oh, I'm going to kill all the humans now. I don't think that's going to happen. I do think that somebody will, program something that is designed to bring chaos and kill people and could possibly end the world as we know it or kill all the people. I do think that that's a possibility, but I think it's going to be purposely planned and not just by AI evolving. I don't think that's going to happen. But yeah, I understand Elon's concern in this situation. Our next clip and our final clip is, what are some of the other issues with autopilot that you're currently working on? And this is a good answer, so let's listen.
Hi, Elon. I have two questions. So both to the autopilot team. So the thing is I have been following your progress for the past few years. So today you have made changes on the lane detection. You said that previously you were doing instant semantic segmentation. Now you guys have built transformer models for building the lanes. So what are some other common challenges which you guys are facing right now, which you are solving in future as a curious engineer, so that we as a researcher can start working on those? And the second question is I'm really curious about the data engine. You guys have told a case where the car is stopped. So how are you finding cases which is very much similar to that from the data which you have? So little bit more on the data engine would be great. So that's it.
Okay. I'll answer the first question using occupancy network as an example. So what you saw in the presentation did not exist a year ago. So we only spent 1 year amount of time. We actually shipped more than 12 occupancy network. And to have one foundation model actually to represent the entire physical world around everywhere and in all weather conditions is actually really, really challenging. So only over a year ago, we're kind of driving a 2D world. If there's a wall and if there's a curve, we kind of represent with the same static edge, which is obviously, not ideal, right? There's a big difference between a curve and a wall. When you drive, you make different choices, right? So after we realized that, we have to go to 3D. We have to basically rethink the entire problem and think about how we address that. So this will be one example of challenges we have conquered in the past year.
Yeah, to answer the question about how we actually source examples of the tricky stopped cars, there's a few ways to go about this, but two examples are: one, we can trigger for disagreements within our signals. So let's say that parked bit flickers between parked and driving, we'll trigger that back. And the second is we can leverage more of the shadow mode logic. So if the customer ignores the car, but we think we should stop for it, we'll get that data back too. So these are just different, various trigger logic that allows us to get those data campaigns back.
Hi.
Sorry, go ahead.
Thank you for the amazing presentation. Thanks so much. So there are a lot of companies that are focusing on the AGI problem. And one of the reasons why it's such a hard problem is because the problem itself is so hard to define. Several companies have several different definitions. They focus on different things. So how is Tesla defining the AGI problem? And what are you focusing on specifically?
Well, we're not actually specifically focused on AGI. I'm simply saying that AGI seems likely to be an emergent property of what we're doing. Because we're creating all these autonomous cars and autonomous humanoids that are actually with a truly gigantic data stream that's coming in and being processed. It's by far the most amount of real-world data, and data you can't get by just searching the internet, because you have to be out there in the world and interacting with people and interacting with the roads and just, Earth is a big place. And reality is messy and complicated. So I think it's sort of it just seems likely to be an emergent property of if you've got, tens or hundreds of millions of autonomous vehicles and maybe even a comparable number of humanoids, maybe more than that on the humanoid front. Well, that's just the most amount of data. And if that video is being processed, it just seems likely that, the cars will definitely get way better than human drivers, and the humanoid robots will become increasingly indistinguishable from humans, perhaps. And so then, like I said, you have this emergent property of AGI. And arguably, humans collectively are sort of a super intelligence as well, especially as we improve the data rate between humans. I mean, the thing like that seemed to me way back in the early days of the internet was like the internet was like humanity acquiring a nervous system where now all of a sudden any one element of humanity could know all of the knowledge of humans by connecting to the internet, almost all the knowledge, or certainly a huge part of it. Whereas previously, we would exchange information by osmosis. We'd have to, like, in order to transfer data, so you would have to write a letter. Someone would have to carry the letter by person to another person, and then a whole bunch of things in between.
All right. I'm not going to comment on that because, I don't think I need to comment on everything. I want to thank everybody for listening to the show. I know this was a long one, and if you made it all the way to this point, please treat yourself to a cookie because you deserve it. If you want to email me, it's Bodie, BODIE at 918digital.com. We'll have a normal news day on Friday, nothing in the middle of the week because this probably took 15 hours total to put out. I started recording at 9 o'clock on a Sunday night, and it is now 12:01 on Monday morning. If you want to chat about this or anything else, you can always email me. It's Bodie, BODIE at 918digital.com. You can find me on Twitter at 918digital. And I hope everybody has a wonderful day. I'm going to get out of here before this podcast reaches 2 hours.